Welcome to the Newton tutorial series. I'm Mike Cruz with AC Tech, and this tutorial is going to be the first in a series of tutorials that discusses how to use the material set library. So specifically, I'm going to be discussing just this group list window. So there are three components to this window. There's this left-hand pane, which has a preview of the material set. It has the grid for auto-generating a set, and also the drop-down menu for selecting the current set. On the right hand side we have two different tabs. The first is the group list that we'll be talking about here. The second is a tab that shows some different plots to visualize the particle set data. So on the group list, this primary grid contains all the clusters that are in the current particle set. So if we change this, we can see that we're populating the grid with the clusters that are in each particle set. Let's go to our 30 to 60 set. There are 14 clusters here that make up this set, and you can see in this panel the current particle that I have highlighted is shown in magenta. So as I scroll through these, we're changing that highlighted particle. So the columns in this grid, the first column is just the number, so you can quickly see how many are in this set, 14. The second is the group type, and if I open up this drop down menu, you can see that all the clusters that are stored in this cluster library, all of those clusters are available in my drop-down menu. So I could have three of the same cluster if I wanted here. 2 overlap 10, 2 overlap 10, 2 overlap 10. Those are all the same cluster in the library, but I could give the cluster a different size. I could call this one 60, 50, and 40. And you can see these first three clusters, same cluster, different sizes. So that brings us to our cluster size column. The cluster size is the total distance across the cluster, the longest dimension of the cluster. So it's not the x, y, or z, but that longest length. And that is how you change the size of the clusters in here. In the cluster creator, you can specify, well, I want to change the XYZ position, the different radii and whatnot. But once you get to the material library, all you're doing is scaling the entire cluster to change that cluster size. So next to that column, we have our material type. So if you recall from the one of the previous tutorials about the material properties, we have three different material types, A, B, and C. So you can define, up to 3 different sets of material properties that can be applied within a single particle set. So what I would do is I'd say, well, I want this cluster to be A, I want this cluster to be B, I want this to use properties C. And you can mix and match however you like right there. Next to the material type is the percent by weight and the clusters per 10,000. So these are directly tied to each other. Obviously, the percent by weight is how much of this cluster is going to be represented in the entire particle set. And the number of clusters per 10,000 is directly used when generating material. So when Newton generates 10,000 clusters, it says, well, we have to have 346 of this. We have to have 368 of this cluster. We have to have 567 of this cluster. And these are tied together such that if I change this from 346 down to, say, 200, that percent by weight is going to change. It drops to 2.2%. So it takes those clusters and distributes them in the rest of the particle set. Next to that, we have 3 columns at the end which you cannot modify. These first 5 columns you can modify. These ones at the end are informational only, and you can't change them. So the sphere radius right here is the largest, I want to say it's the largest sphere in a cluster. That's what it's telling you right there. But if your cluster has identically sized spheres, if they're all 100, then it's just going to be the size of any sphere in the cluster. So you'll notice when I take and scale this up from 60 to 120, that sphere radius just doubled. Back to 60, and we cut that in half again. Next to the sphere radius, we have the number of spheres in the cluster, which, of course, for smaller clusters, we don't really care. But if we had, huge clusters in here, then we might want to be interested in, well, which one has the largest number of spheres. Next to the spheres in the cluster, there's a time step index, and this ties directly into the information that's displayed here. So, along the top, we have a bunch of buttons. So if I wanted to modify this particle set, I can insert a cluster. Let's say I want to insert a cluster right above this 12 cluster. There, we've inserted one. When you click insert, it says, well, let's just take whichever one is highlighted. Let's assume he wants to make another one of that same cluster. And of course, you could go there and say, nope, I want this to be a 27 by 27 or 3 by 3 by 3 cluster right there. Then I could specify my cluster size as being 150. I can set my material type, my percent by weight defaults to 0. Well, we certainly want to make sure we generate some of these, so let's give ourselves 50. And see, because this cluster is so big, even just giving it 50 clusters per 10,000 gives us 10% by weight. Clearly, that's probably a little high. Maybe we only want, let's say, 32. That's a little more reasonable. We can see that my sphere radius for this specific cluster is 18.2. It's a little bit higher than the rest of these. Number of spheres in the cluster is 27, and my time step index. So I can, just like I can insert the cluster, I can take and delete that highlighted cluster. I can go and delete that one. I can go and delete that one. I can take and select and move a cluster up. I want to move this all the way up to the top, or I want to move it back down to the bottom. Equal clusters and equal spheres will shift the number of clusters per 10,000 or the number of spheres per 10,000. So we used to have a column here that was number of spheres per 10,000, but we didn't really use it. It probably wasn't really useful, so we can't really see that data right now. But if I say equal clusters, it's going to take and divide all 10,000 clusters evenly. But clearly, our percent by weights have become pretty skewed because, having the same number of huge cluster, if I still had that other, where'd that other big cluster go? If I still have this huge cluster in here, let's make it 150. If I'd go equal clusters, 50% by weight is this cluster, because obviously 27 spheres times that many clusters is going to give us a lot of spheres. So you generally don't want to be using that. The equal spheres is a little bit more realistic. If I click equal spheres, well, now a couple of these are still a little high, but for the most part my distribution looks a lot better than it did before. Next to these buttons we have a sort button, which simply sorts the clusters according to their cluster size. So if I click sort, it's going to bring this one all the way up to the top and scale it from largest to smallest. Done. If I scale, it will take and scale the cluster size of each cluster by this scaling factor. So if I double it, we'll go from 80 to 300 after we're done. It scales them one at a time, and you can see that they even got bigger in the window here. So 80 to 300, like we said. The refresh set button is simply, well, maybe we made some changes to here in the cluster creator, maybe we made some changes around here. We just want to make sure that all those changes have gotten refreshed before we generate our material. So we'll just click that, and it'll just make sure all the clusters are updated. Now up in the corner, this set of labels is probably the most useful on this page. So basically, these labels give you some general information about this particle set. So when I switch between different particle sets, it's giving me different information for these different sets. So if I go to a 40 to 100 set, the first label is the minimum time step. And basically that's saying that just looking at this particle set and looking at some of the settings right here and here on the general page, it says, well, what do I think the minimum time step is going to be? And based on this particle set, it thinks, well, it's going to be about 195 microseconds for this particle set. If I go to a particle set with larger particles, that minimum time step has increased by approximately the same amount. It's approximately a linear correlation with that sphere size. Right below the minimum time step, there's the particles per 10 cubic meters. So that's going to tell me the number of spheres that would be generated if I generated 10 cubic meters of this particle set, of this material. So going from 40 to 100 up to a 50 to 150, certainly our number of particles has changed. 110,000, 190,000, so almost twice as many particles when I just increase by that little bit. Then below that is our sphere size ratio. The sphere size ratio looks at it's the ratio of the largest sphere radius to the smallest sphere radius. So if I was to find the largest number in this list, 20.9, I think it's 20.9, divide that by the smallest, which would be 19.5, I would get 1.07. So this sphere size ratio you want this to be as close to 1 as possible. Anywhere in the range of 1 to 1.5 is just fine. Even going up to 1.75 or 2 is acceptable as well. But any larger than that, and you're going to start to increase the simulation time simply because you're going to have more particles, more spheres in each single cell in the simulation. And again, to understand that better, you probably should read some papers about DEM and the grid cell and the contact detection methods. But the point is that try to keep the maximum ratio here at around 2. So then these three numbers we combine together to give you a composite approximate simulation time index. The lower this number, the faster the simulation will go. So if I look at my 200 millimeter spheres, that index is 1.5. It's incredibly fast. And that's because these are all huge spheres that are completely unrealistic. And you would never want to use this particle set for a real simulation. You would only use it because, oh, I want to test to make sure I've set up my geometry properly and I've set up my belts properly, and I just want to run a quick simulation in 30 seconds. Even the sphere's only 100 millimeters, well, that's about 16 times slower than the sphere's only 200 millimeters. But I still would never use this in a real simulation because, in our opinion, spheres are just useless in a DEM simulation. That's the entire reason you want to use a cluster, because it has a shape and it won't roll around. So, looking at the simulation time index, we can see that as I go from the 200 millimeter spheres to the 100 millimeter spheres, it increased by exactly 16 times, and I'll explain why that is. So let's consider our 200 millimeter particle. The minimum time step is 1000 microseconds. So when I decrease that, when I cut that radius in half, my time step got cut in half as well. So that means that my simulation to run this particle set would require twice as many time steps just to get to the end as the 200 millimeter particle set would take. Secondly, let's look at the number of particles per 10 cubic meters. Obviously, when I cut my radius in half, that volume of each sphere decreased by a factor of 8. So it's going to require 8 times as many particles to generate the same volume of material. So if I look at this, we've got about 1,500, and 1,500 by 8 is about 12,000. So that's exactly a factor of 8 right there. So the factor of 2 multiplied by the factor of 8 gives us an increase of the time index by a factor of 16. So basically this means that every time you take a particle set and cut it in half, cut the particle size in half, your approximate simulation time will increase by about 16 times. And of course that's only an approximation because there's 100 other factors that tie into the simulation time. But that's just a rough approximation that you can use. And that's exactly the point of this time index, is rather than having to figure out, well, how many particles do I have, what's my time step, what's my sphere size ratio, we just say, well, looking at this, it's probably going to take about if I go from my 100 millimeter spheres to the 60 to 180, it's going to be about 10 times slower to run this 60 to 180 millimeter particle set. And the reason is, look at these sphere radii, these are 30 millimeter radius. My 100 millimeter set has 50 millimeter radius. That's a huge difference in terms of number of particles. We go from 12,000 to 60,000. You know, a factor of 5 times as many particles, but the time step also decreased from 500 down to 288. And the sphere size ratio is not exactly 1, so that it bumps it up a little bit as well. But certainly, I would trust simulation results from this particle set 100 times more than I would trust simulation results from this one. Like I said, the only reason to run spheres is as a pure test case for your geometry. So I would even prefer, if you took this particle set, scale it up by a factor of 2. Boom. Now if we look at this, our simulation time index is 15. This would actually run faster than this. Faster than our spheres only, because our radius is now larger than 50. But I would trust the results from this even more than I would trust the results from this, and that's purely because these are spheres, and as I keep saying, spheres are just, they're not very useful. So I think we need to talk about these checkboxes as well. So if I go back to my percent by weight, let's open up a smaller particle set. If I look at my percent by weight and my cluster count, you might notice that perhaps I want to, perhaps I know exactly how many clusters per 10,000 I want to use. So let's say I know this distribution. I say, well, I know I want to have 100 here and 100 here and 100 here. But if I change this to 100 and change this to 100, well, we're sticking clusters back into that first one. Change this to 100. If I change this to 50, or we're changing these. I wanted these to be 100. So if you check this checkbox, it will hold these cluster counts fixed after you modify them. So I call that 100. Notice the box has become gray. If I change this to 100, it won't stick any clusters back into that box up there. Make that 100, if I make that 100, and I can go through this whole list. But now when I get to this last one, obviously there are only 8,000 clusters left over because we have to have a total of 10,000 clusters, and these are all 100. So I can't manually force this. I say I only want 7,500 here. It says nope, can't do that. There's 8,000, you got to put them somewhere. So if you uncheck this box, you release that lockout on all those cluster counts. Now if I wanted to call this 7,500, it's going to go and distribute the rest of them back into there. So in a similar way, you can modify the percent by weight as well. So if I wanted this 1%, 1%, 1%, 1%. But you can see, again, we kind of have the same issue going on where we're sticking the clusters back up here and artificially inflating these percentages. So if you do that same checkbox, it will apply to the percent by weight as well. However, because of the complex relationship between the percent by weight and the cluster count, it cannot hold it exactly fixed. Because this is simple. We simply keep this at 100 and it'll stay at 100. But the percent by weight directly depends on all the rest of these clusters. It directly depends on the cluster count. So it's harder to hold that constant. However, we can kind of do it. So if I change this to 1 and 1 and 1, you see they're changing a little bit, but not nearly as much as they were changing before. If I go through like this, make all of these 1, I might need to just go up to the top and go through this list one more time. And we can see this time there was pretty much no change, so we're good to go. And of course, you don't want to set all your particles at 1%, but the point is that you might need to sweep through the list once or twice in order to get those percentages to remain fixed, simply because it's more difficult to control the percentages than it is to control the cluster count. So, this checkbox for chain set is simply a flag that allows Newton to know that this particle set is composed of chain links. So if I go to down here, we have a particle set called chain link, and you can see it has 2 clusters in there. We're going to have a separate video that talks about creating chains in Newton. But the point is that I only have 2 links here, and I check this little checkbox so that Newton knows, yep, this is just going to be a chain set. So the percent by weight doesn't matter here because all it's going to do is it's going to generate one link, then the other, then the other, then the other, back and forth. And that is simply a flag that lets Newton know that this is a particle chain. So I think that covers everything on this page. If I recall anything else, I'll be certain to mention it in the next tutorial. But otherwise, if you have any questions about this page that you can't find the answers to in the manual or in these other tutorials, certainly send us an email at info@actech.com. Thanks.